So just going through, starting with 1927, he was born in Washington, D.C. Then, well, he studied physics and mathematics at MIT. He studied electronics in the Navy during World War II. So in the meantime, you could saw some of the photos actually showed his his Navy uniform, right, as a young boy. So, then he studied philosophy at University of Chicago, so he still has affinity to philosophy since then. Learned medicine at Yale University, internal medicine at Johns Hopkins, and neurophysiology at UCLA. He came to Berkeley in 1959 and taught brain sciences. Presently he is professor of the graduate school at Berkeley. He has a MD cum laude from Yale from 1954. He has numerous awards and different distinctions. I just mentioned a few. The NIMH Merit Award from 1990, the Neural Network Society IEEE Pioneer Award from 92. He has been the president of INNS, Neural Networks, International Neural Network Society, 1994, and he's a life fellow of IEEE, so obviously he has the engineering blood in him here. Okay, about his professional achievement, so he authored over 450 articles, 4 or 5 books, depends on what you count, and right. So it's a fuzzy category. Okay, now going to more personal level, so he had 2 wives, right? And 12 children. Yes, one of them is here, though. All right, so we get to the fun part. So 12 children. Some of them are here. So just okay. You can stand up because there will be a lot of stand up from now. So okay, all right. So there are a couple of them for sure. I know, and 17 grandchildren. Okay. Now, going to the scientific realm, so, you know, we are in the network conference, so we talk about the network of researchers. So let's see the scientific family, so to say. So he has scientific children, 58, what we could count, so that are the PhD and postdocs and so on. So 58, that's quite nice. And a couple of them are here. I think we counted 12 of them. So, okay, I don't know, should I name them or you just please stand up? Okay, I think 12 of them are here, so it's, okay, so. That's very nice, and we also counted the grandchildren from the scientific area, and well, it seems to be that as I'm counted as one of your scientific charts, so we try to keep up with you, but presently we count like 50 grandchildren. Okay, so it's a bit difficult to overperform you, I think, even in that area. But yeah, so that's where we are at the moment, and I think that was just a kind of introduction to the banquet speak, and I just returned to Vince. So thank you.
Professor Michael Merzenich from UCSF, leading neurophysiologist. We're delighted that he's joined us today. And Professor Merzenich, would you please say a few words about the lifetime and work of Professor Walter Freeman and the ways in which he might have influenced your work?
So I was skeptical about it, about this being necessary, but it was, my colleague was insistent, so I bought it and I read it. And there was a lot in it I didn't understand. In fact, every time I've heard Walter speak, there was something in his talk that I didn't understand at the moment. and I think that's probably true of a lot of us. But what's amazing about it is that before too much time goes by, you do begin to understand it, and it's almost always true, which is remarkable. But it, for me, was a seminal event to read his book, because it was all about an aspect of my own science that I hadn't thought very much about, and that was dynamics. Now, Walter, to me, is sort of, in my young life, was sort of Mr. Dynamics. Right? And he also appreciated that the brain was exquisitely, inherently adaptable. That it just didn't sit there like a fixed computer with instructions that it had received early in life, in which every neuron more or less knew what to do forever. He understood very early on that, in fact, this machinery was inherently adaptable. And in a sense, when I was a young scientist, that was a very revolutionary, a very uncommonly held religion. Now, Walter got this religion, I'm sure, in part because he chose to study olfaction. That's one of his principal models. And one can wonder exactly where Walter got this idea, that olfaction would be something to focus his attention and life on. And we know that olfaction, in fact, is a remarkable capacities to make distinctions about things we smell. So that a person that is expert at smelling something like wine can tell whether the wine comes from the west side or the east side of an alpine valley in the Piedmont. But they can tell whether the wine from the west side is across the Atlantic, if they're really good, right? The remarkable ability to make complex distinctions about complex combinations of odorants through this machinery. And when you look at the machinery, this makes no sense whatever. There's also an unbelievable, that is to say, from a conventional neuroscience perspective. You just can't have the religion of a visual neuroscientist of his era that saw the world, the brain, as constructing things from little pieces and then combining those little pieces by a series of feature detectors into the big whole piece, grandma or whoever, right? It just was not a realistic way to look at olfaction. And not just was it so fabulously specific with the trashy way it treated its information, trashy from a classic neuroscience perspective, but also had incredible sensitivity, incredible power. So you can take a creature like this one, right? And you can place an imprint on a glass slide, and you can put it among another 100 glass slides, and you can wait a week or two, and then you can distribute those glass slides out on the table, and this creature will find that imprint. And he will identify it as the smell, the combination, the complex combinations of odors that represents a person. And when you think of the weak chemical signal that must be coming from that source, and the incredible ability of a creature like this to make those incredibly complex distinctions, and to make them with such power, given such weak signal, right? And then when you look at this trashy system, which is very sloppy in the way it treats information by the classical view, you realize that rethinking is necessary. And Walter realized this. Walter saw this great conceptual model, which essentially demonstrated that the standard and classical model simply could not hold. Right? Now, it's sort of interesting to a lot of people, to me, that there are still, you could say in the wider world out there, not in this room, the majority of our fellow scientists, even serious scientists among us, still hold essentially to the classic models. Right? So I imagine it must be a little frustrating for Walter, time to time. He probably thought that his ideas were going to sweep across science, right, and quickly dominate everybody's perspective. If you just spoke a little more clearly, that might have happened. Just teasing, of course. But of course, that doesn't happen. This is a revolution. Like the Industrial Revolution, it will take decades, I guess, for the gradual transformation of our thinking and our models and our understanding of this to create unbelievable machinery to make the essential corrections to be on this more correct path of understanding. Now, Walter chose to use this particular animal as his model. Now, for the life of me, I can't understand why he didn't choose audition. We seem to go from that tiny little organ of the front. Actually, if you look interiorly, it's more impressive. One of the things about this organ that's very special is that it has a very complex source of information from an epithelium, in which there are a very large number of odor-specific receptors. And those receptors do a damnable thing. They turn over. And in fact, you can even destroy fairly significant patches of them. Well, I'll tell you a little story. I have a friend at the University of California who's an otolaryngologist. He had a famous wine authority who was a patient of his, who burned out his olfactory epithelium by self-administered cocaine. And so basically he largely lost olfaction, or at least he got to the point in which he basically was no longer professionally competent. And my friend carefully nursed him back to health and said that his olfactory epithelium must be almost totally shot. And was astounded when 5 or 6 years later he saw the man again. And he had very substantially recovered his abilities, he said, and this was demonstrated in tastings and so forth. And he did this with a new epithelium, right? This incredibly plastic system, plastic at every level. To the extent to which it delivers information to the olfactory bulb, it makes combinations of inputs almost immediately in a very, very complicated way. And then when it projects into the prepiriform and the piriform cortex, it projects with an incredibly divergent and convergent projection. It's making very, very complex combinations from the sources of input in the olfactory bulb, which themselves express combinations. Again, you cannot think of a system like this as operating to create this powerful ability to generate this highly specific combinative extraction of information to operate in a conventional way. So Walter looked at this system in operation, and he said, where can this power, where can this specificity come from? And he provided with lucid answers for us in his study of the mass and integrated actions of neurons that are reflected by the ongoing activities in this machine, by its dynamics. That was a great accomplishment in neuroscience in our era. Now, my own parallel crisis was occurring in parallel because I studied animals that had those ears. And I also realized in Walter's wake, in fact, one of the primary things that influenced my thinking about this was Walter and other scientists' precedent studies in olfaction. Because I also had a system that was organized very exceptionally. It made no sense in its organization if you thought about it in a classical way. I created a very elaborate slide which would take me about 2 hours to describe. But let me just tell you what the system does, in essence. It takes information from the inner ear, from a sensory epithelium that's basically a line of sensory cells. Okay, and it delivers it with 32,000 fibers, each delivering a little different message into the cochlear nucleus, and it distributes it there to different populations of cells, which extract different information from this common input. Each one of those nuclei, basically each one of those point sources of information are distributed across the sheet of neurons in the cortex. All kinds of intrinsic dynamic influences enter into the process across these sheets. It does this over and over and over again with different combinations, so that from this information, ultimately, it extracts information in substantially divergent and convergent projections across these sheets in 10 or more nuclear sources. Okay? Each one of them has extracted different information by a combination of the common intrinsic input from the cochlea. It's pressed across the sheet, across the dimensions of the sheet. It's distributing information in time. It's also adding other things in the other dimensions of the sheet. Very complicated business, beautifully structured stuff. It makes various combinations from the two ears. It adds various kinds of intrinsic information. And it makes something different in 10 nuclei out of that base incoming information. And then it does an absolutely insane thing. It throws it all together in an all-to-all projection anatomy to layers of neurons in the inferior collicus. But from in that level, when you look in the inferior collicus, you actually see emergent order. So you move across these layers in any direction. I saw this first about 1980. It actually, from this crazy anatomy, it generates highly specific topographies, orderly changes of parametric responses of neurons across these sheets. So that makes a certain amount of sense. It's done some powerful extractions. Don't know exactly what it's for, exactly what it means. But then when it projects to the next level, it does it again. It projects in an all-to-all way from across these sheets to another set of layers across the next level. Again, if you look across that level, you see complex topography, more complexly extracted information, and then it does it again in the projection into the cortex. Combination upon combination upon combination in abstraction. And now when you look at the cortex, you say, well, what would be the resultant of that? You know, this must be something powerful must be happening here that I can make sense of. A friend of mine of many years, Maurice Goldstein, decided as a young scientist at Johns Hopkins in the biomedical engineering department that he was going to resolve the basic functional organization of the auditory cortex. He had a wonderful young collaborator that worked with him for a number of years, Moshe Aviles, a fantastic experimental scientist and theoretician. And they reported from the auditory cortex of cats for a number of years. And their notion was that they would look in every possible way with the parameters of sound delivered into the ears of the cat, unorally and binaurally, and they would resolve what the cat is making out of the complex projection, anatomy, and organization of this powerful system. And after about 4 or 5 years, Moise had basically left the field. He left the field in a sense because it was too damn complicated. He never saw the same thing. Right? Every neuron seemed to be interested in a different, odd, complex combination of inputs. And every parameter he poked, he saw selectivity. And that was co-selected, and all kinds of interdependencies with parameter changes in other dimensions. It was too damn complicated. When I was a young scientist, I thought that I would enter this and clear it all up, enter this discipline. I hadn't read quite enough of Walter to realize how foolish this was. And to make a long story short, I would see beautiful structure in a cat. Structure in which the animal is clearly sorting information in very powerful ways across specific parametric dimensions. And then I'd look at 3 or 4 more cats and not see a sign of it. Right? Well, it began to occur to me, I'm a little slow, but it began to occur to me that maybe all cats aren't alike. And maybe what a cat has done with this auditory cortex and with its hearing has something to do with that. That maybe I'm looking at a continuously adaptable machine, as Walter appreciated his machine must be. Now, I got another chasing when I was a young scientist, when I worked in the development of one of these devices. And this is a cochlear implant that was originally created and engineered in my laboratory at UCSF. And now it's commercially sold and distributed by a company called Biographical, which is a division of Boston Scientific. That sounds very wonderful, doesn't it, commercial? This is a quite sophisticated electronic device. It's the most complicated electronic device implanted in humans. In fact, this very model of implant is the most complicated device implanted in humans. Now, the whole principle of this device is to simulate the input delivered from the ear to the brain. Right? It's to fool the brain to thinking in an ear that's so damaged that it can't basically excite a still surviving auditory nerve array that is delivering input across its sensory, right? So the problem in most deaf individuals is the destruction of their sensory organ, but the nerve still survives. So the whole idea is to simulate the input. Well, I worked for quite a few years with my colleagues doing complicated experiments trying to perfect the simulation of input. And we reached a very low level of perfection. Well, think about it. We're shocking 8 or 9 or 10 or 12 or 14 or 16 sites around the spiral form auditory nerve array, right? This is a little bit like playing Chopin with your forearms, right? This is crude. And of course, when you shock anything with electrical stimulation, you excite axons more or less simultaneously in time. Now, we became a little bit more sophisticated. We could get a little more dispersion of activity in time. But the patterns we generated are nothing like the normal patterns. So you can think about this in another way. You can think about it as the basis of a grand plasticity experiment. We're going to take a different form of input that is basically, may I use the word shitty, right? Really lousy, really crappy, right? We're trying our best, but it's lousy. And we're going to introduce it into the ear and by the simulation, and we're going to cross our fingers. And that's essentially what we did. Now, let me say that when we did that, we did represent information across channels using what's called a channel vocoder, a voice coder, a vocoder, using the principles of engineering and communication engineering at the time. And so we were appropriately distributing and evolving the information. There was hope that the person could initially hear lousy stuff and ultimately they could make sense of it. And actually, when we first implanted these in deaf patients, there was almost no sign of it. What did they hear? Well, they described it as something like a radio that was just not tuned onto the station. Or it sounded like a robot. And they did not like the sound in general. They didn't like the robotic speech. They didn't like the mistuned radio. Well, 3 or 4 or 5 or 6 or 7 or 8 months later, they hear everything. And not only do they hear everything, they have very high levels of speech reception. Okay, so it's common if you run into one of these people, in about 95% of these patients, they actually operate in their language ability so that it's sometimes difficult to tell that they've ever had a hearing loss, right? They can talk to you on the telephone perfectly reasonably. They can talk to you perfectly reasonably with your back turned to them and so forth. So many of these patients achieve speech reception rates approaching 100 words a minute. Very accurate, very rapid speech reception abilities. Now, this is occurring basically with inputs that are delivered in an alternative form, right? So, in a sense, the phonemic structures of language have to be reconstructed, right? But they are successfully done so that the utility of hearing is established. Now, let's think about this for a minute. What does it mean to reconstruct the representation of the phonemic structure of the language? Well, the brain is there, sitting there, and if the person has acquired their deafness, and now we've applied this input in a new form, in their earlier life, they had developed language abilities. They had developed a syntax and a vocabulary and understood the meanings of things. They had memories for things they heard. They used the hearing of speech to guide their speech, and so forth. So you could ask a simple question. Would you expect there to be a seamless connection with this new representation of the details of what they hear, with all of that stored stuff? I submit that the classic view, you would not, right? You just wouldn't expect it. The reality is, it's seamless. The correction is perfectly and beautifully integrated with all that was there before. And although that's another way of saying the only way that can happen is if the brain is powerfully contributing to this recreation of phonemic structure. It must be intrinsically and fundamentally participating in the recreation of this phonemic structure. Now, I was going to make another point about cochlear implants, and I don't know if this will work, so this is a risk. You can reduce speech dramatically, as one of the former postdocs that worked with me in cochlear implants, Robert Shannon, who's now a professor at the University of Southern California, did. And you can do that by basically, and you can demonstrate that speech can still be intelligible. And I want to play you a little version of that. And this is not just modulating noises, This is a little bit more complicated than I'm going to explain that in a minute.
Walter Freeman is a great guy.
Okay, we heard a phrase, right? We all agree with that. Okay, now here's... I'm sorry, I'm going to go back again. So this is...
Walter Freeman is a great guy.
Okay, now I'm going to simply represent the signal by dividing the spectrum into a series of... a noise spectrum into a series of bands. And I'm going to modulate each of those bands with the energy envelope that applies to that part of the spectrum. Okay? And that's what we're going to hear next. Now you have to listen carefully and see if you can understand. You have a little bit of cueing that's already occurred. I want you to listen one more time. Now if you practice this a little bit, this very degraded signal has no really useful spectral information in it, right? It's all envelope stuff. It's actually interpretable by your brain as speech. And actually, when your hearing is very degraded, for example, when your inner ear really goes to hell in a serious sensory nerve deafness, this is basically the kind of crap you're receiving. But it's still useful. It's still mostly intelligible, despite the paucity of information that's being delivered. I want to show you a completely different form of speech in which scientists have completely removed envelope information. This is from a study that came from Brian Moore's lab at Cambridge. In this case, you could say high-pass the signal so that all of that modulation is gone. Now he's only representing, in the high-pass, you could say there are little moments of little events in the signal that mark the changes of variance that are occurring in the signal that we might expect will generate little pulses of correlated activity that mark those events. And that's basically all this is providing to the brain, right? And let's hear what this sounds like. It turns out that you listen to this for a while, it takes 2 or 3 days, and speech in this form is totally intelligible, right? Now let me tell you something that happens with cochlear implant patients that hears this kind of stuff. They not only say ultimately that it's intelligible, they understand everything, they say it sounds perfectly natural. It sounds just like it sounded when they heard it perfectly, right? So they ultimately identify it as being the natural signal that they've heard before when their hearing was, if their hearing was intact. Now actually there are several other manipulations that I could make in this complex signal, and it would still be intelligible to you. I make this point to say that the brain is not stuck with having a simple single strategy for extracting information from complex signal. You can think of it this way. When the brain is young, it's all about details. It's building a construct of language sounds and of speech and of meaning from sound by its extraction of the details. But ultimately, through its powerful powers of correlation, it's going to be able to extract information. And it's not really taking in information and cut across this signal at different levels. And that's valuable to us. It's valuable to us to be able to read signal in this abstracted form for the sake of completeness and for the sake of scanning and paying moderate attention. And then when it's really important to us, we focus down on the details. I want to say one more thing about this. The first form of speech I played to you is almost trivially disrupted by noise. Any real disturbance of the envelope, of course, will degrade it to the extent to which it's not intelligible. This form of the signal is almost as noise-immune as actual speech, presumably because we're generating little strong pulses of correlated activity, little ringing oscillations, maybe Walter Freeman you, that are creating those crucial moments of activity. This form of speech is remembering. If you look at an oral speech memory test and deliver speech in this form, you remember what you heard with almost normal ability. When you listen to modulated noise, it's only very poorly remembered. And a person's memory abilities are very deficient. So I have another example there, but I'm going to go on. And finally, this machine is massively plastic. And that's been a long interest of mine as well as Walter's for a number of years. It's easy to drive the cortex to be powerfully selective for complex. It's easy to create feature abstraction as if feature extraction was really that big a deal, Walter. I agree with you on that. It's easy to create massively selective responses of cortical neurons by engaging cortical neurons in behaviors that make something of complex inputs, like with the acoustic input at the top, as you can see it's on the vertical and across the azimuth of this time. Here we have a little piece of sound that's like a little piece of European emergency sound. Very grating sound. It consists of a series of phrases that are upflights. I can make this input important to the animal specifically by coupling its use with a signal from the limbic system. And I can do this in a number of ways. A signal can be dopamine, a signal can be acetylcholine. In this case, it's acetylcholine. Okay? So I can deliver acetylcholine each time I deliver this little complex piece of sound to the brain. So I'm having that convergence between this action of the limbic system and this complex input. Now, if I look at a naive animal, which I see at the upper left, I'm looking at all the places where neurons respond at all to the signal. And when I look at the middle blue bar, the horizontal bar, I'm looking at a signal file from all those sites, right, to that signal. And you can see they respond weakly to the first phrase, and then with a scattered and not very useful response to the rest. And now I simply make that input more important, you could say, by pairing that input with a signal from subcortex that refers to its meaning, and I generate a large area where neurons respond to it. And now I see a strong response to initial event, and I see strong and almost unattenuated responses to the following phrases. And I look at those responses, I see that they're actually selective for the specific features of the stimulus. They want upwise, they like 10 minutes per second, they like things changing at about this rate of in frequency and time and so forth. So powerful plasticity, powerful changes can be induced by this magic combination of both cortex of inputs that are modulating those changes and inputs of signals that are conferring, you could say, meaning through inputs that are delivering behaviors. I want to just say briefly, because I was stimulated by the last talk this afternoon about one other experiment that we're doing at the moment, because it relates very specifically to, you could call it a kind of Freeman experiment. Basically, we have an animal that's trained, this is a rat, to recognize the occurrence of two successive sounds. The initial sound is delivered against several foils, and the second sound is delivered against several foils. So any one of a number of sounds can be delivered, followed by a second sound, which can be the right or a target or non-target sounds. And the sounds are delivered with a particular temporal structure, and there are also foils that are significantly different temporally, right? So we trained an animal to do this for a while, and after 3 or 4 or 5 weeks, the animal is very proficient at making these distinctions about this particular temporal succession. And now we look in the cortex in the animal and reconstruct the selective representation of sound frequencies. The animal's been seeking a sound that has a particular spectral content. And we see, in a sense, an exaggeration of the representation of the initial sound reflected in the cortex. The cortex is very strongly biased for its representation. And it sits there, you could say, to the moment that we initiate the analysis of the selective response of the cortex. It sits there with that bias. Now, this is the most important thing that's been happening to this rat for it's all its food for the previous 5 or 6 weeks. It's not so surprising that it's biased for the reception of the single sound. And then we deliver that initial sound against all of the other foils. And we look forward in time. All the other foils. And we look forward in time. And what we see is that the cortex changes its selectivity across the time. And it becomes powerfully exaggerating. It powerfully exaggerates its organization for the second sound. Not just any second sound, not the foils, but the second sound, that is the target. That is to say, it's as if the system is wired in the expectation. Not the expectation that the foil can occur, because it is also expected to occur. So it's a combination of expectation and predicted reward. Right? So in a sense, it's a kind of convergence between how Walter has talked about that and what we heard in the last talk. Now finally, we've applied our evolving understanding of brain plasticity and brain dynamics to create training programs for prepare children and adults. That's another way of saying that all of the science Walter has had such a critical part in it has a practical extension. And I've been fortunate enough with many young and old colleagues to pursue some of those practical extensions. And basically what we're trying to do is steer the cortex that's in various degraded or underdeveloped or distorted modes of operation back into corrective directions insofar that's possible. In children that are language or reading impaired, in children that are autistic, in individuals that are schizophrenic or have bipolar disorders, in patients with age-associated decline, bipolar disorders, and so forth. And we've actually had powerful impacts in all of these populations by using these principles. And one of the things I want to say about all of these training programs is that when you improve perception, almost invariably, you improve action. And let me give you a simple example of that. If you train a child as a listener, and we've trained, in May of this year, we'll train our millionth child. When you train a child as a listener, if the child is impaired, you commonly drive relatively large-scale improvements of their listening accuracy and abilities. So if you give them something like a language battery that includes a subset of tests that define their listening accuracy, you see that all of those subtests are improved. And there's some overall gain in their listening. If the child sits initially one standard deviation below the normal median at the 16th percentile, they'll advance on average to about the 60th percentile. Okay? And what's really interesting is that they advance just as much. There is no significant difference in their expressive behaviors. They talk more fluently, they talk more powerfully, they can translate what they hear into verbal action with more facility. Improvements in perception in most of these training regressions lead to improvements in action. And finally, I want to say that one of the things we commonly see when they improve is, insofar as they improve, we recover gamma band coherence in activity in the cortex. And this is a simple example of that. We can see differences. One of the ways that they're impaired or different neurologically is in the weakness of their coherent gamma responses. And this is an activity that occurs loaded in a memory-based listening task. And suffice it to say that the pre-training kid sits in the red line at the bottom, and you can see that there are significant differences in the gamma frequency range between controls and pre-trained kids. And then when kids are trained, you recover gamma coherence. And when you recover it, there is a strong correlation between its recovery and the recovery of accuracy in speech reception abilities. And between the recovery of accuracy and speech reception abilities, not just the quiet, but the talk. So, I have to say that I've stolen from Walter all my life. And I have to say that I have learned as much or more from Walter than from any other scientist. He is in my pantheon of the very smartest people that have contributed most. And we are a community of scientists. Everyone in this room has something to contribute in this community. But some people just do it more often and do it more profoundly. And Walter is one of those people that I've learned from over and over again. And I'd just like to thank him, not just myself, but I suggest we all raise a glass and toast Walter and thank him for his many contributions and his recognition. Last, I want to say one last thing. Walter, here's to you. Now, I want to say one last thing about this. I only wear this tie on special occasions or funerals. And I want to say, Walter, it just cannot slow down. Walter, we still need you. Hang in there, buddy.